Okay, so I don't see many faces that were there yesterday to the introduction to grass. Who was in the introduction to grass? Okay, only 3 people. Wow. I don't know if that's good or bad. Let's see. So first note, in this lecture, I will be going through GRASS as an engine to process Earth observation data. Okay, so what in GRASS is called imagery. At the same time, we have a session where Phong is also using GRASS, but in an HPC context. So there, you'll see things more related to parallelization and scheduling, etc. So if you're more interested in that, yeah, I'm quite happy if you, in the 2 minutes, you move to the other room and go and check Phong's presentation. Okay, other notes. So I planned these lectures in a way that you would have some time for hands-on to play around with GRASS and try to figure things out by yourself. And yeah, this didn't went exactly as I expected yesterday. Not that it went bad, but yeah, it's a bit of a cold start and we don't have so much time. So this lecture, I will still be giving you some time for you to experiment, but I will give you the solution to the exercises right away so that you can immediately try to implement or try to achieve the goals in these exercises. So I've made a lot of, quite a good deal of workshops and lectures using notebooks, and I started these lectures with the notebooks, and at some point I decided to go back to the slides in the spirit that we would be more in a classroom environment and that you could experiment with stuff. So I hope that this still works. This creates a bit of a challenge here for the multimedia team. They are expecting more like a tutorial where someone sits here and go through a bunch of code. So this will be a bit different, but I hope that you can still profit from it. So let's see. Who of you has GRASS installed on your system? Okay, we have not that many people, but I think about half. So those of you who haven't installed for whatever reason, I suggest that you get together with someone that has the program installed, okay? So let's wait a few seconds for that to happen. Good. So now let's see. So since very few of you went to the introduction to GRASS yesterday, in principle, that means that every other person here has interacted with GRASS before. Is that the case? Who has used GRASS before? Okay, that's fewer people than the ones that attended the lecture yesterday. Okay, so yeah, so I'm not going through today through the concepts to the basic structure of GRASS and its file structure, data structure, etc. So that was yesterday. Let's see that if you can still follow this lecture like that, okay? But if you have the program installed, then the recipes I've here, they are relatively simple to follow. Okay, so this is an overview. I guess everyone can read this, big enough. Just that I'm on the way. Okay, again, this lecture is meant for people that have some familiarity with GRASS, that you understand at least the internal structure, and that you have, at least fired up the program a couple of times and understood how the different interfaces work. Beatrice, I'm hearing a lot of echo. I don't know from where. Maybe, wait a minute. Test. It was actually my laptop. Didn't block that. Okay, sorry. Anyway, you can then cut these bits, I guess. All right. So we have here a number of goals, but what I want you to take home after this lecture is an overview of what GRASS offers in terms of imagery processing. Imagery, we're talking again of Earth observation products, aerial imagery, and stuff that you get out in the wild. in your GIS system. So we're going to go through ways of obtaining this data, correction and display, image classification, which is a big chunk of what usually people do with Earth observation, and then we'll have a glimpse at time series and other advanced methods that you have available in GRASS. And also, I want these slides to remain as, let's say, a reference for future work. So GRASS is this, let's say it's a rabbit hole, right? We have in GRASS almost 500 modules natively installed with the system. And then you have the add-ons, and the add-ons are a few hundreds more. Today, we're going to use a few add-ons. So this is a rabbit hole, and no one has GRASS in his mind, right? You have to always go after the modules and understand how things work together. And I hope that from this lecture, you get the reference that in future work, you can back and see, okay, so how do I do image segmentation? What kind of methods do I have available? And you have here a short reference from which you can start your work. Okay, so imagery in GRASS, and the three of you that were there yesterday know these are the modules that start with the character I for imagery. Okay, they are some of these are quite old, and as you will see later in this presentation, or as the presentation goes on, it was shaped a lot by what it was. This kind of work, let's say 20, 25 years ago, when Landsat was probably the most interesting product, and then MODIS, but it's still quite a useful toolbox. Now, of course, when we speak of satellite or imagery or aerial photography, at the end of the day, these are rasters in our system. And that means that most, I would say probably all the modules that are meant for rasters, they also apply to this kind of data. I hope that's clear. And yeah, and then we have the add-ons. And the add-ons, they provide different functionality, but most importantly, you have modern add-ons that provide you access to the state-of-the-art imagery sources, such as those that result from the Sentinel program. And there is a particular add-on called iSentinel that we'll use quite a lot in this session. Okay, so first, the data, right? You can't do anything if you don't have some data to start with. And these are some of the pathways to access data. First of all, the module are in Goodall. This is, we didn't saw this one in particular, but those of you that attended the lecture yesterday know that there is a collection of modules just for data input. And this one, since it uses Goodall, as the name implies, it also gives you access to the internal functionality that Goodall provides to access different Earth observation sources out there with different let's call them APIs. And then we have a collection of add-ons that you can install on GRASS that provide you a simple interface to other sources out there. One is IEODAG. I myself, I never used this API, but it's relatively popular to access Earth observation data. And then we have specific modules to access Sentinel, Landsat, and MODIS products. Okay, we'll see a bit of Sentinel later on. And again, these are add-ons. Yesterday, did we saw that? No, we didn't saw that how to install, but we'll see it today. How to install an add-on. Okay, so that's where we start. First task, so this is not an exercise. The first thing that you need to do to follow on with this lecture is to get a bit of a sample data set, okay? This sample data set is on the same location of the test data set that we used yesterday, so they will overlap, as you will see. And we'll then import that data with the iSentinel module. So again, I'm putting here right away the QR code to a code snippet that you may then use to achieve this task. So this lecture was meant for those of you already proficient in things like rgrass or GrassScript to do these tasks in your environment, being it R or Python. But anyway, as we can see, so not that many people are proficient in Grass. You may also just use directly your command line, your toolbox in Grass to achieve this. So can everyone access this snippet? Yeah. So okay, so I will give you now a few minutes, see if you can achieve this task. Okay, is that fine? Okay, hands on then. So it will take like 3 to 4 minutes to download the data set, maybe less than that, and then other 3 or 4 minutes for the data import. Okay. So who has managed to download the data set? Okay, already a couple of people. So Is this big enough? Can you read what is in the screen? So I have here I opened the snippet, okay? And I will now, yeah, complete the task. Again, a lot of copying and pasting, but I prefer it this way, that you have your time also to do these things yourselves. So, okay, I have already downloaded the data set this morning, and now I'm going to start GRASS. I'm starting it from the command line. You may also start this from the user interface, if you will. Okay, so starting immediately with an error. That's funny. Okay, so those of you that were in the lecture yesterday, so launching GRASS from the command line, it again launches the familiar user interface. Okay, and we can go back to that then a bit later. So the first thing I will do is to create a map set for my Sentinel data sets. Okay, and for that we are using here the -C switch for the map set module. Next, I'm going to install the iSentinel extension. And it's with this module g.extension. We spoke about this yesterday a little bit, but we didn't saw it working, but it's just like that. You just give it the name of the add-on you want, and it gets installed. So you might need some of these add-ons, they might need compiling, etc. In this case, it's a relatively simple thing to install. So now we can use the iSentinel module to list the files that were in this data set that we downloaded. Okay. Yeah, so it's not called Sentinel-2. Let me see. So I probably use a different name. It's only called Sentinel. So I will rename. Okay. And I will rerun this command. And what it is doing, it is printing the available bands in this folder. Okay, and it uses here a pattern. So this is probably a regular expression, not probably, but a regular expression. So it's looking for the bands 2, 3, 4, and 8 from the Sentinel data set. Okay, and now I'm going to use the same pattern to import this into my map set. And let's see, I hope, is this big enough? I hope so. So here, what is different here? So we have a parameter limiting the memory used by this module. And also we are providing here a file name called timestamps, and this will create a log of the data sets imported. Okay. So let's see who was able to run the listing command. Yeah, you have, and you're getting something different from me, right? Mm-hmm. Yeah, so I'm getting here something different. Yeah. Mm-hmm. And then did you manage to run the import? Ah, it's still running. Okay. So let me do something. Okay. So I think there is some issue with the folder on which I downloaded this this morning. So I will run this again. Mhm. Okay. Yeah. So running many things several times in the same folder sometimes gives you this. So who has got to this stage so far besides you? What's your name, by the way? Vey. So who's got as far as Vey? Vey, sorry. Okay, I hope you're still following. So I'll go and check a little bit again. Okay, so let's see, where are we so far? So two notes. So the import module is giving a few errors because it cannot find some mask files. Yeah, I don't know exactly why this is happening, but I know it's not a deterrent. The other thing is that the folks that are working on Windows, these backslashes here, they won't work. Okay, so you have to delete the backslash and put the command in a single line, and then it will work. Okay. So I saw a number of people who are already getting far with this. That's good. So let's see. My Sentinel import already completed, and now I can list the maps that were imported, and we have all of these. So these are all in the same region of space, let's call it, and we have different timestamps, and we have those 4 bands that we talked about. So this is infrared, red, green, and blue. So infrared, it's band 8, red 4, green 3, and blue 2. And now what we'll do, something very important, and those of you that attended the lecture yesterday know, which is to set the region. And actually, we're setting the region to one of the raster data sets that are in the North Carolina data set that we saw yesterday. Okay, so now let's look at here at the user interface. And if I do a reload, now I have here my new map set called Sentinel-2. I hope, yeah, this is visible. I have a big screen. And if I expand, I have here all I think they are called scenes in Sentinel. I prefer to call them maps, but that's the GRAS jargon. Okay, let's pull one of these. And now it's always important to remember that this is just one band. So GRAS by default uses this color scale to display raster data. So we are not really looking at the colored image, okay? So for instance, this is in QGIS would be a grayscale, which probably is a bit more intuitive. Okay. So let's see who managed to download the data and at least get the list of the of the different scenes. Who managed to do that? Okay, a couple of people, and those that haven't, yeah, I saw many people getting very close to that. Let's see. Do we have questions so far? No. Okay, so let's move on. So then we'll use this this data in a couple of exercises further on. Okay. In QGIS, I don't think so, Tom. I don't think so. So you won't be able to visualize this data that was imported into GRAS in anywhere else. So in this case, what we could do, for instance, is to also display something from the North Carolina data set. So we had the elevation, right? And this is the elevation that we imported yesterday, right? So this is all data that has been pre-prepared by the GRAS people to make our lives easy. All right. Very good. So you can do that. This little button here, and we can use one of these set color table menus. They are not that user-friendly. But later on, we'll see how to display a true color image. Okay, and I think that's something more interesting. So this kind, this kind of color table definition, it's something that you could do in any kind of raster file. So you can assign a different color scale. We'll see also with vegetation indexes how to do this. Okay, so let's talk a little bit more about what grass can do. So first thing to recall is how this whole thing is working. So we have a sensor up there in the air or in space that is transforming usually a signal in the electromagnetic spectrum into a number. Okay, for instance, it can be a band of light, or in most cases a band of light can be radar. And so there is a certain energy, a certain radiance that is hitting the sensor, and the sensor discretizes that. We have a continuous signal that is discretized into a number. And then depending on the sensor, you might get this radiance translated into numbers in 8 bits or 16 bits, and that gives you more or less resolution. And this number, this digital number, may be transformed to radians. So you are encoding something, a physical variable, a physical entity into these discrete numbers, okay? And you have tools in GRASS that allow you to do this. So you have, if you have a raw satellite image that is just the numbers that the sensor translated, you can transform that into radians, okay? And we have these tools, Landsat 2AR and Aster 2AR. And you can also use R MapCalc if you know the particular relation between the digital number and the radians. Usually it is a linear relationship, okay? So as you can see here, it's not by chance that we see the names Landsat and Aster here. So these were things that were common in older days of Earth observation, right? Where the services were not as refined as we have today. If you're using Sentinel, you don't need to worry so much with this, but it's an important set of methods that you have available in GRASS. Then after that, you have to correct for the influence of the atmosphere in this radiance and the effects of the terrain. This is something that is still performed by the main missions and sensors providing this kind of data. And you can also do this in GRASS. And especially with the module @correct or @COR, and that supports many different sensors. So it's quite a proficient tool. And you also have ways to correct for topography. And again, also for Landsat, you have a special module to identify clouds. So these days, if you access data from Copernicus, a lot of this has been done for you. You don't need to worry so much. But if you were working with other sensors or with historical Earth observation data, all of this might come handy. Okay, so now let's get to more GRASS-specific stuff. So in its internal working, sometimes it's useful to group some of these Earth observation data sets into groups so that you can bulk process satellite imagery. And this is used in things such as rectification, so based on control points on the ground, auto-rectification, clustering, and also in image classification. So you can do bulk image classification this way. Okay, and I leave you here the main modules to do this. And then the semantic labeling. So with semantics, you're giving meaning to all those numbers, right? Not only for the data that you acquire from a particular sensor, but then to the products that you create from transforming that. And labels, they are also useful to filter groups of imagery. And here are some of the tools that allow you to do this. So we have band library to print the existing labels. You have semantic label to assign labels, and then R support, and an important one, MaxLink, that can assign labels during segmentation. So if you're working especially with aerial photography, an important step in the processing pipeline is the georeferencing. And there are different ways of doing this, most often with control points in the ground, but also by co-registering with existing maps. And we have tools in GRASS to do all of that, such as iGroup, iTarget, GCP, Rectify. And there is also the orthophoto module, specifically for the orthophoto generation with digital elevation models. So this again, I don't know, it depends on how long have you been in GIS and Earth observation. So back in the day, this was a very important task or a very important duty of geographers, was to produce orthophoto maps. But these days we have better and better sensors in space, and yeah, this is not as crucial as it was in the past. Okay, so let's talk a little bit about display. So again, we have to keep in mind that we have this very relatively narrow bands of the spectrum that are being sampled in the sensor, the different bands. And then what you would display would be an image like I showed you before, but you can make compositions. And this is something that, since the time of Landsat, is one of the staples in Earth observation analysis. Okay, some important modules to keep in mind. Colors enhance. So this does some kind of, how is it called? Balancing. It's not balancing. Yeah, it applies the histogram to make a more visible image. And then we have the modules in the D family that, for instance, uses 3 different data sets to the 3 different RGB channels, okay? And there's also the histogram that displays an histogram of an individual channel. Okay, so next exercise, let's print a true color composition out of the data that we just imported. And I think that in the interest of time, I will just execute this and then check whether you can follow me or not. Otherwise, you can go immediately to the snippet, try to do it yourselves, and we'll try to do it together. So a bit of an exercise here with the microphone. Could everyone take the link to the snippet? Yeah? Okay. So the next snippet, it's this one. Okay, so again, if you are working on Windows, mind here the backslash, so you have to put this in a single line. So here we have, so we are using this display commands, and because of that, I will have to create a new display window. Okay, I'm not going into much detail about this. That I can then show you in the GUI how to do this. Okay, so I create a new display window. Here it is. Let me send it to another place. And now I'll use the colors enhance. And colors in ASA, that's the word I was looking after. It's a kind of equalization method that happens here. And I'm giving it already the 3 data sets on the red, green, and blue. So bands 4, 3, and 2. And on the same timestamp, yeah, and on the same location. Okay. And now I can use the RGB, and this is displayed here. Okay. So here we're starting to see features that look familiar, like crop fields, roads, etc. Let me zoom in a little bit. Yeah. So this is the basic stuff once you import this kind of data. This is 10 meter, yeah. Sure. Yeah, you can't really see houses. Yeah, but almost. But roads, you can see them quite well, even the smaller roads. And yeah, there are some structures. I don't know if they're probably not fences, but maybe walls around crop fields. I don't know. It's quite detailed. So who has managed to get this? No. Okay. And what's the problem? Okay. Let's see what. Yeah. It's probably better if we move on. Let me just show you that here on the user interface in the layer stack panel, we have here the icons to add data, and one of these is called add various raster map layers. And this is basically, for instance, you can have also an HIS layer, but here we have this menu at RGB map layer, and this does more or less the same does the same that the RGB. The only thing here is that it doesn't do the equalization automatically. Okay, so let's see. Did anyone? Did anyone manage to get this far? To get this this image? No. Okay, at least one person did. All right. Anyway, you can after the lecture you can also come to me if there is a particular issue particular area that you can't move off, or then you can come and ask. Okay. So this is another interesting activity. This also comes from the years of Landsat. So Landsat collected several bands, also red, green, blue, infrared, etc. And it had a panchromatic channel. So it was capturing a longer or a wider segment of the spectrum, and being a wider segment, it could capture that in a higher resolution. And so you would have, like, imagine the RGB bands in 30 meters, and then you have the panchromatic in 10 meters. And there are methods that you can apply that resolution afterwards to the individual channels. And this is called image fusion, and you have a few modules that allow you to do this in GRASS. And also there's this Brovay algorithm and a PCA transform to do this with PanSharp. Okay. Yeah. Again, these days, since we have sensors like Sentinel, this is not so useful anymore, but yeah, something that you can do. Okay, now let's get to the products. And one of the oldest products that people did with Earth observation data were the vegetation and then later the water indexes. Okay, in most cases, these are relatively easy to compute. So they are simple algebraic functions like NDVI. And for that, you can simply use our map calc. Okay, so you're doing a simple raster calculation. But you also have specific modules for that, like IVI. And IVI computes many different things, including also NDWI. And then we have the rcallers module that applies a caller table to the outputs. Okay, so that's the question that Tom had earlier on. And rcallers is again its own rabbit hole with lots of presets, so you can do a lot of stuff. Most of the time, you're just assigning a pre-existing caller table to a particular output. Okay, so let's do another exercise. So now we're going to compute NDVI and then DWI with IVI for this particular timestamp. And since we have band 8, we use that as near infrared. And then we'll add semantic labels. And we need to set a color table for NDWI to display it. So here is the snippet. You just have a sip of water while we copy it. Oh, sorry. Okay. Shall I move on? You have access? Okay. So that one is here. Right. So this is the first command here with IVI. And right, it's pretty simple. Okay. You give the bands and give it the output. And you use this VI name parameter to instruct which index you want to calculate. Right. So at this stage, pretty simple stuff. Oops, didn't copy. Okay, yeah, and then pretty fast. Okay, this is a relatively small area, but usually these are things that don't take so much time. And so GRASS is very efficient in this kind of cell-to-cell computation. So now I'm using R support to provide a semantic label. So, so with this now, we have a proper name, a proper identifier for this output. Now we'll do the same for the NDWI, and basically I change here the name of the index I want to compute, and I give it, of course, a different kind of input. In this case, the green channel and the near infrared. Okay, good. And again, our support to provide the label. And now I am applying a color table to the NDWI. Good. So now let's go back to our interface. If I go here to my Sentinel map set, reload the maps, and I have these two new maps. Okay. Let's hide all this and let's see what happened. So this is the NDWI. And as you can see, there are some lakes, right? And here the value will be above 0. Yeah. And then we have the crop fields and the cities. Let's see what we have computed there. So here, this looks like a crop field. minus 0.5, and then an urban area, still negative, but not as negative. And we can also have a look at the NDVI. So this is probably a bit more familiar. So very green, where we have more vegetation. And then we have this kind of pale colors in urban areas. So let's click here on an urban area, so a number closer to 0. And then, I don't know, this might be a forest. So a number well above 0.5. Let's see, who has worked with vegetation or water indexes before? Okay. Yeah, so this is a very common kind of exercise, right? Good. So who managed to compute this with IVI? Okay, yeah, okay, there are not that many, but some people are managing to follow. Good. Good. You didn't, Faye? No? Okay. But you see the maps showing up here in your user? Okay. There's some mystery there to be unraveled. Yeah, and you don't get any errors. So my guess is that you don't have the region set correctly. That's typical. And those of you that were in the lecture yesterday, so that's a typical thing. So maybe you have a region that is so small, or the region might even be empty, and then the computation just does nothing. Okay, so try to check the region. So one of the ways, you can go here to settings, computational region, show computational region. Okay, and then you will see this red. If I take everything, see this red, usually square or rectangle. Okay. So, and if you don't set it properly, or maybe set outside your work area, yeah, it computes, but it's not really doing anything, right? So again, those of you that were here in the lecture yesterday, and also for the rest of you, for early GRASS users, this is a very common source of, I wouldn't say error, but a source of issues, that the region is not set correct. Okay, and like, imagine that Faye would now go on this course asking, oh, my IVI is not computing anything. The first reply would be, have you checked the region? Typical. The elevation is in, okay. That's a curious. So you don't have the data set used yesterday, right? That's one of the reasons why it doesn't work. So my suggestion, so you are trying, you set the region with something that doesn't exist and it failed. So what you can do now, you can set the region with one of the maps there. It will be slightly different, but it's okay. All right, so let's move on. Let's see how we are with the time. Okay, so now image classification. I think this is really the main course in Earth observation, right? Who agrees with that or thinks that this is all nonsense? Who has done image classification? Okay, quite a few people. All right. So again, these are things that exist in GRASS for many years. Different methods out there, and also more modern methods. So we have methods to do the classical radiometric classification, both unsupervised and supervised. And yeah, I'm not going to tell you the names. You can read. And then you can combine radiometric with geometric classification, and here you have the GenSig set and the SMAP modules. Okay, yeah, Feng is getting somewhere. I like that. And then the object-oriented classification, which is also no longer yeah, it's still kind of state-of-the-art, but it's not the novelty that it was at some point. And you can also use machine learning methods for this. And so this is, again, another rabbit hole. We could easily have a full lecture on these methods. And those of you that have some understanding of machine learning, I think this will be recognizable. You have modules to split your data into training and validation, then a module to learn, and then another to predict. Okay, the typical pipeline. And in GRASS, you have different algorithms that are implemented: random forests, gradient boosting, logistic regression, etc. So this is really a rabbit hole. If you want to do image classification with machine learning, GRASS has a lot to offer. Okay. Who has ever done that? Who has ever applied machine learning to image segmentation? Okay, Feng, yeah. All right, yeah. So this is nothing so exceptional. Okay, we have now, I think, a little exercise with this. And again, I will go through it, the copy and paste thing. And yeah, what is noticeable here? So we're going to use iSegment. So this is one of the modules that does, and let's see, this was unsupervised. Let me check if I had this correctly. Yeah, this is object-oriented, unsupervised object-oriented classification, iSegment. And yeah, with some parameters like minimum object size of 100 cells, and then a relatively low threshold. So we're going to have many different classes, and the restriction to memory. Oh, sorry. And one of the outputs is the goodness of fit, and we are going to display that because it's also an important product that you can inspect the accuracy. Let's call it, maybe not accuracy is the right word, but the effectiveness of your classification. Did you manage to copy this? Yeah. Okay. Let's go again to the copy paste business. All right. So we start with glist. So those of you that were here yesterday, do they remember what the G family does? Yeah, it was too long ago. Sorry, a bit louder. Yes, exactly. So that's the modules that manage your environment. Okay. So in this case, glist is just listing the data sets that, in this case, are of type raster and comply to a particular name pattern. Okay. In this case, we are going to list all the maps in a particular timestamp. This is going to create this file. I think I can show you the file here. Yeah, so the file just contains these names, okay? So now I'm going to feed that file to iGroup. And I'm telling iGroup, please create a new group called S2 with a subgroup called S2 from the contents of this file. Yeah, and then it informs the group and subgroup that it created. And I can use again the iGroup module to inquire on the contents of this group with the -L flag. And there you have it, a simple list. Okay, so now we can move on to iSegment. And the interesting thing here is that I'm giving it just the name of the group. And this is going to be applied wholesale on these 4 bands. Okay. And then I provide the constraints that I referred earlier, the output, and then also a map with the goodness of fit. Okay, so this is pretty simple stuff, I would say. So let's see what this does. Takes a bit longer than the vegetation indexes. Anyone managing to run this? Okay, good, good. Right. So let's see. It did 15 passes. I'm not sure this always runs the same way. Should. Okay, now I'm going to use our Univar. Can you guess what this does? I don't know. No, we didn't refer to this one yesterday. So it computes univariate statistics on a particular raster. Okay, in this case, it's on the goodness of it. Let's see. So this is anyone here that works with Goodall, for instance, directly to inspect raster data. Yeah. Okay. So this is similar to the output of Goodall, right? Yeah. So yeah, we have here let's call it basic statistics of this particular output. What we can see, so we have a mean of 3 nines, okay? So apparently this is working very well. And the standard deviation is also relatively small, okay? So apparently this was an awesome segmentation. Shall see. Okay, and now I use again the rcolors module. And assign a color table to this output. So let's look how this, or let's see how this looks in the interface. Reload maps. So here they are. So let's first look at the result of the segmentation. Again, so I think now I already seen these before, but it's kind of expected. So we had the threshold was a low number. So this would give us a relatively high number of objects. But still, with that, well, let me check again, because I don't know it by heart, with the minimum size of 100 cells per object. Okay. So let's zoom in. There are some interesting features here, like for instance, it's kind of crossroads, or it's crossing between two highways. It's managed to identify the highways quite well. Yes, Tom? Yeah, yeah. And this, yeah, yeah, yeah. Yeah, that's true. So it had 4 different bands as input. It had 15 passes. It's a relatively small area, but still it's quite fast, right? And some of these methods might not be easy to parallelize, both in terms of spatial extent, but also in thinking about the different objects that you create in an algorithm like this. An algorithm like this, to speak the truth, I don't know exactly how this could be parallelized, but it's not as simple. It's not like parallelizing a map algebra exercise. There, it's pixel cell by cell. That's very easy to parallelize. Here, it's a bit different. Right? You need to be aware of the number of segments that you're creating, etc. So it's not a simple exercise. But at the end of the day, that the answer to that question most of the time is resources, right? If there is someone that invests in this, maybe you can get some kind of parallelization in. Okay, I don't know. Maybe it's an exercise for a master student. Maybe it's part of a PhD thesis and it's implemented here. And a lot of the add-ons that are coming into GRASS, they are the result of research. So that happens. So did this little dialogue with Tom make sense? Do you understand what's going on here? Yeah. I guess especially those of you that already worked with image classification, this is not so strange. Right. Right. Any other questions at this stage? Yes, please. So for sure it's an iterative process, right? But what we can do always is that we come here to our toolbox and we can go to the manual of the iSegment module. And maybe here we can find an exact answer to that. Okay. I know that this is an iterative process. Okay, and you can even, for instance, you can even limit the number of iterations. There might be a default. Let's see. Iterations, no, there is no default. So there is some kind of stop condition. Yeah, but there you have this long description of the method. Okay, and again, you know, I said this yesterday several times, and it's very important also that here in this session you get this perception that the manual is one of the most valuable things of GRASS. Okay, every single module has a manual like this. In this case, iSegment is quite a deep process that is here implemented, but it's described also in depth. And like this question, I don't know it by heart. Not this, or most modules I don't know by heart how they work internally, but you can easily in the manual understand this. And then not only understand how it works, but also to tweak it in a way that suits better your use case. Okay. So you learn quite a good deal of stuff just reading the manual. All right. So now here, like you get, for instance, different examples. Like here, for instance, you are generated more or less a higher or lower number of objects. Yeah, and then in the end, I also showed it yesterday, but I can show it again. So we have things such as C also. In the C also, you have GRASS modules that do similar things, or that are usually used in together with the current module, and we have the references. In this case, it's interesting that we don't have actually a scientific paper. I would expect in this module to see a scientific paper, although, yeah, again, image segmentation with object-oriented segmentation is quite powerful, but it's not new. It's quite old already. So maybe that's a bit of that. And here, for instance, we have a link to the source code online. Yeah. So that's one of the messages that I wish you to take home, is that the manual itself is a resource, an important resource. Okay. Any more questions? Yes, Fink. Probably. Probably. And yeah, and I won't say more than that. Again, yeah, we have 1 hour and a half to go through a field that in itself is quite wide, from the physics of the sensors, the physics of the atmosphere, the electromagnetism, to these methods that transform the Earth observation into useful products. So this is a wide range of fields. For sure, I'm not the most knowledgeable person in it. I've done work with Earth observation for a long while. I was doing, 20 years ago, I was using already image classification programs for whatever. But you know, as not only here, but as in any other domain, you know, you need to understand what you're doing. You need to study so that you use all the power of tools like GRASS to your advantage. Yeah. Okay. Well, time is no longer on our side, but yeah, who is finding this useful so far? Let's see. Okay, still people raising their hands. That's not everyone is asleep. Okay, good. I hope. Yeah. All right. So I think, yeah, image classification is one of the most important things, or the most important, perhaps. Although yeah, we saw interesting applications of Earth observation this morning also. So this is all going also well beyond this more classical methods in GIS. So what do we have more? Okay, other tools. Evapotranspiration, right? Who works with evapotranspiration? Has worked with evapotranspiration? Okay, a few people. So this is, again, we are getting now to particular application domains, right? I don't have an example. I just want you to understand that you have quite a number of options, different methods that are available in GRASS, especially with this evapo module. And also we get here to very specific things such as the heat flux and taking into account the root zone soil moisture. So Tom can explain you what that is, right? So again, keep in mind that this is a large tool chest where you have a lot of things to choose from. Energy balance. So again, this is focusing on forestry, agriculture, and you have different tools there. For instance, to compute net radiation, very interesting. And I think soil heat flux, yeah. Yeah, so this is a different method than the one that depends on evapotranspiration. Anyone here working on soil besides Tom? No, or agriculture? Okay, we have one person there. So you know what this is. Does it ring a bell? Soil heat flux, does it tell you something? Yeah, okay. So you have to go and check the manual and see if this is useful. Okay. All right. So the last slot now, it's about time series. So time series, they are a unique family in GRASS. So there's a whole family of modules to work with time series. Okay, so yeah, these days people call it sometimes data cubes. And we have, first of all, different tools to create a time series, and then many tools to transform and work with time series. So, and basically, there is also a little exercise further ahead. You register a set of maps with timestamp, and it becomes your time series. Oh, and we get immediately to the exercise. So what is here the goal? The goal is that we have these different timestamps in our Sentinel dataset. So it means that we can compute the vegetation indexes at different points in time. If we do create beforehand a time series, you can do all that calculation in bulk. Okay. And there is this like this wildcard. I don't know if you say that. We can also see that as an animation. Okay, so let's go quickly through this. This one would be, in any case, a challenging exercise. End of the day, people are tired, and it's a long exercise. Would be anyway a bit difficult for you to get there only on your own. So it starts with the tcreate module, and it is just creating a new time series, and it gives this name, Sentinel-2 North Carolina. And now there's a little bit of a trick. If you remember in the first task, when we imported the Sentinel data, we added this timestamps file as a log, as an output talk of that import. And so I can use that now to create my time series, right? There's a bit of a trick here, okay? Yeah. By the way, let's see what's in this timestamps file. I actually don't remember. Yeah, so this is kind of, looks like a kind of not CSV, pipe separated data. So we have the name of the file, the timestamp, and then the band. And somehow this is sufficient here for t-register to get it. Okay, so now we can use t-info if you recall from yesterday, we have this family of star info. So we have R info, V info. The info does the same, but for a time series. And it's going to tell you things such as, well, when was this time series created? What is the time span? In this case, we are looking at scenes from the first 6 months of 22, spatial extent, and etc. Okay, and yeah, we also have a bit of semantics here. Okay, then I have here this T-rasts list, and let's see what this does. So it's listing the contents of this time series. It's very similar to the timestamps file. And here I'm looking into just a subset of this. So with the input. Right. So we are looking at particular, no, not a particular timestamp, but just the band 4. Okay. So let's then do the NDVI computation. So let's see what is happening here. So I'm providing the inputs. So band 2, no, band 8 and band 4, of course. So near infrared and the blue, I think, yes. Name of the and the name of the output. And then what happens is that I'm not using an existing module that computes the index automatically. I'm providing the actual NDVI expression. Okay, and doing this with MapCalc. So there is a particular version of the MapCalc module for time series, and what it does, it is going to apply in bulk this particular expression to the time series. All right. So let's give it. Yeah, it's amazingly fast. Although, okay, small data sets and cell-by-cell computations, but still fast. Okay, and now the traditional stuff. Let's do apply a color table to this. And see here we have this is a preset NDVI, and it applied to the 6 time points that exist in the time series. Okay, now last but not least, let's try to do an animation with this. It's going to launch a new window, and it doesn't work. Yeah, it had to be at the very end that something wouldn't work. Ah, it's frozen. Okay, the window itself is frozen. Did someone got to this stage? Yeah, is it also getting? Whoa! So that means it's not a problem with my. Yeah, I thought this would be like some library missing or something. And my CPU is getting. Maybe it's doing something. Let's give it a few moments. So let's go back to the presentation because we just have a few minutes left. Let's see what else did I had. Oh, this is the last slide actually. Let's give it a few seconds here. I think something is being computed, but doesn't look good. Okay, so who feels tired? Yeah. Yeah, that's natural. Okay, you still have 3 days to go, so take care of yourselves, right? So let's see. What I want you to understand. Okay, we talked already about the manual. So you have this large tool chest from which to pick different methods and to do a lot of experimentation. Really, so this is really a tool for scientists. You have so much to try and to experiment. And then again, for those of you that were here yesterday, and even for those that weren't here then, this is all very easy to automate then from R, from Python, or even from the Bash shell. So today, with my original idea would be for some of you to be implementing this maybe in a Python script or in an R script. Yeah, it didn't happen, but that's not so hard, and you can always go back to the documentation from yesterday's lecture if you want to know how that works. So as always, yeah, I think something wrong here with the animation. Let's leave it. Okay. So I leave here a few links. Image processing in graphs. This is a part of the online manual. Is kind of a gateway to many of these methods. And I leave you here our links also to 2 notebooks. These notebooks are quite deep, so they would be for long lectures of several hours. And this you can also get a bit more detail on these different methods. And finally, there's the GIS book. It has a lot of stuff about imagery, so a whole section, not chapter, so set of chapters dedicated to imagery processing. It's also a good resource out there. Yeah, I see 2 minutes to 5. Any questions, comments?